Okay, so welcome everyone to the ICTS String Seminar. Today we are very happy to have Subir Sachdev from Harvard telling us about random TJ model theory of the cuprate phase diagram.
So yeah, well, thank you very much. Yes, can I start? So it's great to be back in India for the second time this week. There's a previous seminar I gave at IIT Madras on Monday, which was more stringy oriented. This will be more of a condensed matter type talk. Well, I shouldn't say stringy, it was more quantum gravity type oriented. All right, and I hope, I'm glad to see things are getting better in India and also here in Boston. And I hope I'll be able to visit this fall as I've been planning for some time. Okay, so I'm going to talk about the TJ model and its implication for the cuprate phase diagram. And I recognize I'll try to reach a broad audience here, and please don't hesitate to interrupt me with questions. So let me just give you the essential physics that I want to focus on. So this is the phase diagram as a function of temperature and hole doping of a compound like yttrium barium copper oxide. There's lots of complicated things that go on at low temperatures, let's say below 100 Kelvin, including superconductivity and various other phases down here that I'm not showing. But even 100 Kelvin is a very low temperature here because the natural scale of the interactions is more like almost 2000 Kelvin. And my focus in this talk will be entirely on what happens, let's say, above 100 Kelvin. And if you look above 100 Kelvin, there seem to be, it seems like just one big metallic phase of some type. But there's very important differences, and there's really three types of metals. One is the conventional Fermi liquid, where basically if you start from free electrons and do perturbation theory, you will get the correct answer of many details of the electron spectrum. Then there's sometimes called the pseudogap metal, which is a metallic phase in the sense that transport looks metallic, but with a much lower density of carriers than a Fermi liquid. And so there's complicated issues on something called the Luttinger theorem, which tells you that, in fact, the size of the Fermi energy, for example, the size of the Fermi surface should be the same as in the free electron gas. That's a crucial theorem of condensed matter physics, and that seems to be violated in this metal. And finally, in between, we have a strange metal, or now being called a Planckian metal, where the characteristic time is independent of the strength of the interaction and just given by temperature itself. Okay, and this Planckian metal seems to be associated with some critical doping, PC, which is now being determined by various methods fairly accurately in many compounds. And so there's so roughly speaking, this kind of scenario we have is you have some pseudogap metal where the Luttinger theorem is violated, a Fermi liquid where it is not, and then some quantum critical point near PC, which determines this Planckian metal physics. Okay, so my focus will be entirely on these three different metals. Okay. However, I'll just show one experimental plot of this is NMR data from last year from the group in Paris. And what they see by measuring NMR is that previously there'd been some detection of glassy spin-like behavior where the spins freeze into static configurations. I'll talk about this a bit more later. But what they found when you applied a magnetic field, that this glassy behavior extended all the way to PC. So this spin glass type behavior is something that's present in the pseudogap regime. It's an important characteristic of the pseudogap. Okay, so that's the title of their paper. At the pseudo, up to the critical point, you see this hidden magnetism. Okay, so that's an experimental, very short introduction to a very confusing set of experiments. But what is the theoretical model we'd like to solve? Well, the theoretical model itself is also extremely simple, and I'll write it down now. So you have a square lattice and it is in the parent compound at P equals 0, you have 1 electron per site. So this is a certain concentration of oxygen or dopants in the material. And these electrons are frozen in their charge, but their spins have this antiferromagnetic arrangement. So this is an insulator, and the spins have this staggered structure. Now, this is a classical ground state. Quantum mechanically, there's exchange between the spins, so there'll be fluctuations of this type of some amplitude J. So there's a J term which flips the spins around and also likes them to be antiferromagnetic. Then when you dope the system and you remove some of the spins, then the electrons can move around, and there's an amplitude for the electron to move, which is called T. And so now you have the electrons moving around. However, if two electrons try to occupy the same site, that's in the TJ model, you're going to forbid that. So that's really the key important thing, because that makes it a much more complicated problem, this local type of repulsion. Okay, so that's the basic model, and this is what we'd love to solve on the square lattice. And many of us believe, and there's, I think, a lot of numerical evidence that if you solve this type of model, you will basically understand the broad aspects of the experiments. Okay, all right, so there's been 30 years. This is not the model I'm going to solve. There's been 30 years of work on it. I'm going to solve a highly simplified model. Even that we won't fully solve, but the hope is that the highly simplified model still has the basic physics that we hope to describe. All right, so let me write down in terms of a few equations. You have fermions that have a spin index and a site index. In this case, I've written it having n sites. This could be on a square. For the cuprate, that should be on a square lattice with some fixed value of T and fixed value of J. The spin operator is just this bilinear of the electron operator. This is how you define P. And the most important point is this constraint, which says that you cannot put 2 electrons on the same site. So on each site, there are actually only 3 states, which I've shown here: the empty state, the spin up, and the spin down. All right, so this is the model we'd love to solve for the Tij and Jij uniform in the square lattice. And this is the model I'm going to study. I'm going to take Tij and Jij to be just random numbers with 0 mean and mean square value T and J. Okay, and we've made, I think, substantial progress in understanding this. This is, as you, of course, this is what's now called the SYK model was originally the SY model, which was this model at T equals 0, which is this term at P equals 0 also. Anyway, so that was a model, we studied in '93. And then the T model was added, also later work by Parttime and George, and there was quite a bit of work of this in the '90s, early 2000. We understood a lot of things, but the way we analyzed it that way wasn't quite right as far as the doping was concerned. And now, of course, there's the new SYK model, which is a slightly different model, which I won't present today, but it has a certain structure of critical solutions that are now much better understood. And so now we're kind of going back to the original model that we really wanted to understand and seeing, how much of the new progress can be applied.
Subir, can I ask a question at this stage?
Oh, sorry.
Yes, please go ahead.
Is there any intuition why randomizing coupling captures the same physics besides the solubility part? Is there some idea why?
I have a slide on just that point, so let me return to that in a minute.
All right. Okay. Thanks. Thank you.
Yes,
sorry, Subir, just to make sure. So this is no longer nearest neighbor hopping or spin-spin interaction. Is that right? It's
so here's a picture.
Okay.
Yeah. So here you have n sites at random positions, and any electron can move from any other one site to any other site. You forbid double occupancy, and any pair of them can have a spin exchange J. So it's all to all and random, right?
Thank you.
Okay. and the most important point, which makes it different from SYK, is this term here, this local constraint. That's entirely missing from SYK. If you look at this term, this is sort of like SYK, because it has 4 Fermi operators here. And this is like what's called the Q equals 2 SYK. So without the stop, this is Q equals 2 plus Q equals 4 SYK. And in that case, we know that the Q equals 2 term always wins. And this just becomes a Fermi liquid at low energies. Okay. So if you just took SYK without the stop, this term always wins. And at low enough energies, it's a Fermi liquid, and at higher energies, higher temperatures, there is some strange metal Planckian behavior. And all of that's been studied in great detail. In fact, was studied in the old days too. And that's really not what the phase diagram looks like. So we have to, so the main part of my talk is that once you put the stop sign, it starts to look very much like the experiments. Okay.
Just question?
Yes.
So the stop is basically no double occupancy, right? That's the constraint.
Correct. Yeah.
Right,
Yeah.
thanks.
I have a question. Hello.
Yes,
so,
go ahead.
like, since it's antiferromagnetic and also it's all-to-all, I'm kind of confused. What is the stop really doing?
Well, I mean, this is the model. I mean, so Jij is actually both ferro and antiferro. It's a random number with 0 mean. You can put in an average value of Jij, and in fact, that gives you superconductivity. We'll have some papers on that. But this is the model. There's some, it's the TJ model with this constraint. This is part of the model we're going to study. Or you can imagine that there's another term here, a Hubbard U term. In fact, that's the model that's also been studied recently. You add another Hubbard U term, and U is very large. So as U goes to infinity, this becomes, this constraint is imposed.
Okay. Thanks.
About this Q equal to 2 and Q equal to 4 SYK, there has been recent works which claim that when T is very large, okay, the Q equal to 2 term is very large, it sort of becomes like a many-body localized phase. But you were saying Fermi liquid, it becomes Fermi liquid there.
It's a slightly different model. Yeah, so there is a transition to many-body localization. That's in a different basis where the randomness is not all-to-all. It's slightly different.
Oh, okay.
I'm not going to consider that. Okay. That's a slightly different model. Okay.
One more question. May I
yes,
have
please.
If J was not random with 0 mean, would you have normalized the J term by 1 over n rather than 1 over under root n?
Yes, that's correct. Yeah. So the normalization is chosen so that the energy is extensive. The total energy has to be of order n. That's how you choose the normalization.
Okay. And does this make this system different from a non-random J problem where J is not random?
Well, that's a very difficult question because we don't know the answer to the non-random J problem. That is the problem we'd like to solve. Mm-hmm. But we're after, okay, there's no shortage of papers, including by me, on the non-random J problem. Mm-hmm. And we think we understand what's going on there too, I think, at least. But okay, what I think the J model, this random model will achieve, let me just say it, that was just the next slide. It's a nice toy model, which we think we are getting close to agreement between numerical studies and analytical studies. And that's important because then you know what you're doing is right. And also, okay, as I'm going to say, it's still maybe even be physically relevant. So why study this model? As many people already asked. But first of all, The real system is not a perfect square lattice. There's impurities, there's all the dopant ions, there is disorder. So you see that in the system. So it's not all-to-all randomness, but there is randomness in every sample. Number two, we have introduced randomness, but not in a way that it leads to some exotic thing like many-body localization. This is a kind of model where everything self-averages, so every site looks exactly the same as any other site, even for a single sample. So it's not as if localization and other many-body localization is somehow taking over because of randomness. So randomness simplifies the problem, removes the distractions of many things that happen at low temperature, which this model certainly won't get right. And then this is also what I meant. So numerically, this turns out to be a very easier model to study because you can, instead of taking bigger and bigger samples, you can average over many samples. And that gives you the thermodynamic limit in a much faster way. So, you know, there's enormous effort on studying the TJ model of square lattice without randomness. At best, you can do about 20 sites, I think, these days, maybe 20, 25. But then there are so many things happening when you change size from 20 to 25. Things are not smooth at all. And so you don't know what the thermodynamic limit is. Here, it's quite simple. And finally, I will show you, I give you evidence that the basic physics that I mentioned, and you know, which was the, say, physics above 100 Kelvin, where you have a Fermi liquid at high doping, a pseudogap metal at low doping, that is a metal with low density of carriers, and a Planckian criticality with, in fact, SYK-like behavior in between, which is also seen in experiments. All of this is present in this random TJ model. Okay, so I think that's another reason to thoroughly understand it. And then that will be helpful to study the more realistic model. Right, and of course, you know, I guess there's been a lot of work in high energy physics recent in the past year or so, where people are averaging over different conformal field theories because they have simpler gravity duals. But the philosophy here, you know, which goes back to a lot of old work that we've been doing in this area, is basically that once you have a system where there's a lot, you know, where there's chaos is a modern way of saying it, or we would say where the quasi-particles just totally decay and everything is kind of dissipative, then the system is very strongly self-averaging. So you may as well study a system where you know, it does the self-averaging for you by just averaging over many samples. So it gives you a greater access to a regime of strong correlations. All right, but you know, these are all motivations. There's no guarantee that this would turn out to be useful, but I think it is being. I hope to convince you. Okay, so I'll begin, and this is not the way the work was done, but the most recent work, in fact, is numerical studies. And let me just I've defined the model. Let me just tell you what we know about this model from the computational work. So this is exact diagonalization work and also kind of DMFT-like work with Monte-Carlo, done basically at computers at the Flatiron Institute with my students and various postdocs at the Flatiron Institute. All right, so let me summarize the phase diagram that appears from the numerics. I'm going to show you a lot of numerical data, but I can imagine, given this audience, that I will lose a few people. So let me just take my word for it. This is what the numerical data shows. So I'll just on this random TJ model. And in fact, this basic phase diagram was in fact predicted by us in this paper with Darshan Joshi, who's a postdoc at Harvard. And you get, so this is what you get. So first of all, at high doping, you have a Fermi liquid. So in a Fermi liquid, you have a constant density of states. And all the correlations in the random model are just on site. So you don't have to worry about any Q dependence. You just look at local correlation functions. So the Fermi uncorrelated decays is 1 over tau. This is just the Laplace transform of a constant. And there's a constant density of states at the Fermi level. And so that's what you get for a Fermi liquid. And the spin correlation function, well, the spin is a bilinear in the C. So it's basically the product of two G's, where G is this guy. And so it goes over the square of that, 1 over tau squared. And that's actually generic to any Fermi liquid, even without disorder. That the local spin-spin correlation function will decay as 1 over tau squared. On the other hand, at low doping, you find the spin correlation function goes to a constant at long time. So this means that the spin remembers its initial orientation for essentially an infinite time. And that's what we call a spin glass. The orientation is different on different sites. So here, the specific realization of the disorder will matter. Each realization of the disorder will have a different spin orientation on different sites, but it's constant, whatever it is. This is also metal. There are mobile charges, but with a smaller density, but that's enough to give you the 1 over tau decay. Okay, so this is nothing surprising. These are just basic characteristics that I'm reviewing, but you do find by numerical study, as I'll show you, exactly these two phases. And moreover, what you see right in the critical point is the thing you would find if you just did the naive SYK analysis, which in the previous model without the stop sign was only present at rather high temperatures. Here it's present down to 0 temperature. But only at a specific doping or a small range of dopings. And so its characteristic is that its decay of spin is halfway between this and this. It's a 1 over tau. And this 1 over tau is related to, it's basically the square of the 1 over square root of tau decay of the SYK correlator. And I'll show it. But it's a little subtle how we understand this, and that's what was the content of this paper. But for now, this is what you see, and this is what you get from just taking a naive SYK model with spin. And so now let me just show you all the numerical data with all of this evidence. Also in the Fermi liquid, there's a Fermi energy that obeys the Luttinger theorem, and here it doesn't. You might be a little bit worried about what do you mean by Luttinger theorem in a system with disorder? Well, there is a generalization of it that's been known. And whatever that generalization is obeyed here and not obeyed here. Okay, so that's an overview of what the numerics taught us. And let me just show you the data now. So there's a lot of messy plots, and it may not stay with me all the way through, but let me just show you. So if you measure the spin correlation function, this is from exact diagonalization of 700 samples as a function of doping. You measure this object and you then compute its spectral density, which is chi double prime of omega. So in a spin glass, this goes to a constant, and this spectral density would have a delta function near 0 frequency. And that's what you see at small doping, say p equals 0. There's what looks like a delta function developing here, and that's the signal of spin glass order. But as you increase the doping, you go up here, you see the spin glass peak goes down, and say around at this doping around 0.4, it's pretty much gone, and you have this, this linear omega dependence over here. And then when you go to even higher doping, it becomes, this peak basically disappears, and this kind of non-analytic omega dependence disappears, and that's what happens in a Fermi liquid. But this, so that's the spin glass. This red line is SYK calculation. I'll show you what calculation it is in a few minutes. And it seems to be, a very good match. The scales have been rescaled to fit this, so there is one fitting parameter. But still, it's got this structure where it's a discontinuity at 0 frequency and then a linear omega dependence. Okay. What I'm going to argue is that this linear omega dependence is a signature of a boundary graviton. So there's evidence for this graviton in an actual TJ model that from this numerical work. Okay, so this is a way of measuring the Fermi energy. I won't go into any of the details.
Since you said it, I'm sorry. By boundary graviton, do you mean the time reparameterization modes of the JP model? Is that what you meant? Sorry.
Yes.
Okay, thank you.
Yes, exactly that.
Okay, thank you. Thank you. Sorry.
I'll say a bit more about it. I mean, I said a lot more about it in a more general context on Monday. So,
Sorry,
yeah. I mean, nothing you don't know.
Thank you.
Okay. But yeah, so this is pretty exciting to see this, without any large M limit, or here M refers to SUM, as I'll explain in a minute. Okay, so you see this kind of SYK-like behavior, not just the leading step discontinuity, which is the 1/tau decay, but also the subleading term. Okay. This is the Fermi energy, as I was saying, and what you find is that you see that when the blue and the black dots are the same, then Luttinger theorem is obeyed. So let me just say that without explaining it. And it seems to be, again, until around 0.4, it's obeyed, and then it's not obeyed when you presumably enter the spin glass phase. This is the DMFT work, the quantum Monte Carlo work by the Flatiron group. And so they see, this is a slightly different model. They have a finite U. We had a U equals infinity. And they see, again, a spin glass phase and a Fermi liquid phase, and they can map out the finite temperature diagram much better than we can from the numerics, from the exact diagonalization. And what is this colors, these strange colors over here? Well, what they measure is the spin-spin correlation function. And they fit the data to this form and get the exponent theta. So this is what's done over here. The SYK exponent is theta equals 1. That's just the square of the fermion Green's function. So what you see is that theta equals 1 is this line over here, is right at the critical point. And on this side, it goes to theta equals 2, which is the Fermi liquid value, and seems to, spin liquid, it just goes to 0 essentially, because it doesn't decay. All right, so this is really, very exciting evidence for SYK criticality between these two phases. This is in the Fermi liquid phase. They're measuring the coefficient of the Fermi liquid behavior. This omega squared behavior and T squared is characteristic of a Fermi liquid. And so there's a characteristic energy scale, and that vanishes as you approach this critical point. So the Fermi liquid theory is completely breaking down. And you're entering some entirely different phase via this SYK-like criticality.
So, sorry, Subir, please forgive me. I'm a little lost. In these plots, are they simulating the model you described with the random averaging, or is that the model that's being simulated? Sorry.
No. So maybe I should spend a little time. I should have explained this. Thank you. So in this data, what we do is we take a sample with a given Jij, we diagonalize it and measure whatever we want to measure, and then repeat with many sets, few hundred samples. So here we explicitly get the full spectrum for SY, this PJ model with random T, random J, and then repeat many times. So that's what's done here. Okay. So this is, we get all kinds of real frequency, real-time data from it. This calculation is very different. So what you do here, maybe I will stop share and show this on the board behind me. Okay, so I will show this here. Okay, hopefully you can all see the board. Right, so you start out with a model. Let me so Z is some integral over the electrons, exponential of some random T and some random J and so on. And then you average the whole thing.
I can't see it.
You can't see anything.
We cannot see.
Yeah, sorry.
I'm sorry.
Sorry. Maybe I should have. Where's all my pens gone? Here's another one. No. Oh well. Okay. I can't take too much time to hook up my iPad. Let's see. Somebody took my pens away. Oh, there they are. Okay. Can you see that?
Yes.
Okay. So you have Z, and you have some integral over the electrons, and here you have some Lagrangian for the TJ model. Okay. And then you average over this thing. So when you average over this thing, as you know, you get some kind of G sigma action. Well, here you get something analogous to that. There's an integral over dG, and there's an integral over dQ, where Q is a spin-spin correlation function. So it's a 4-point correlation function. And so here, then you have exponential, right, okay. Yeah, so there's some effective theory for L of Q and G, which is sort of like the G sigma action for the SYK model. Now, however, the important point is that here, we do not have a closed form expression for this. You can just write down the G sigma action is trace log plus Q4 or something like that for the SYK model. Here, for this model, we don't have a closed form expression for this. So what you have to do is you have to solve a single site Hubbard model. So you have to do this following path integral. So this is the fermion path integral, just integral over C. And it's a path integral with, C dagger, dC, d tau. But there's also terms like, there's also.
Sorry.
Yes.
Have you already taken the large limit here,
yes?
And you can't
yes,
find even at large even at the large
yes,
you can't find a closed form. Is that
correct? Correct. That's
okay,
why it's so hard.
Okay.
Yes.
Yeah. I guess you can't sum the planar diagrams in this model so easily.
The point is that there is this U term, C dagger, C, C.
Yeah.
And then there'll be terms that depends on Q. There'll be like C dagger, G inverse C, and there'll be C dagger, C, Q, C dagger, C. Anyway, so the point is what you have to do, which is what's done in the numerics. You pick a G and a Q, pick some G of tau and Q of tau. Given a G of tau and a Q of tau, you have to then evaluate this path integral. And then you make the whole thing self-consistent, okay? Now, what you do in SYK is that this next step is very simple. If you give me a G, I just compute the path integral over C is just a determinant, free fermion determinant. So here, the free fermion determinant is replaced by a Kondo problem. It's something like a Kondo problem, which you cannot solve exactly. So what they're doing is all of the quantum Monte Carlo is evaluating this thing. In place of the free fermion determinant, you have to solve a strongly interacting problem because of the local constraint. Okay. All right. So you could all see that. So that worked. Good.
Yes.
All right. Now I have to share back. Okay. Yeah, so I was showing you how you get SYK-like behavior near the critical point. This is the breakdown of Fermi liquid theory from the large doping side. This is, again, this Luttinger theorem. They also measured it in a different way. And again, very consistent with our exact diagonalization results. You find it holds all the way up to the critical point and then totally goes haywire. And this is the...
no, sorry, if it may, the statement that you're making in this previous slide is just the same statement that the quasi-particles become very short-lived, right at this curve. Or is that in the previous slide?
Yes.
Failure of
this one, yes. Yeah. So here we're showing the quasi-particle becomes short-lived.
Mm-hmm.
So this is the non-quasi-particle critical point. Now on this side, this particular method, they cannot access the spin glass phase. but we can access it in our exact diagonalization. And also from our theory, we expect the quasi-particle to re-emerge on this side, okay, but with a smaller Fermi surface. So we have some evidence for that, some theoretical calculation. That's still something we are continuing to work on and fully sort out what's happening within the spin glass phase. But yeah, so the quasi-particle breakdown only happens at one point or a small window, and you can't tell from the numerics. It's just a point or a small window.
Okay, thanks. Yeah.
Yeah. So and what this data is showing you is not quasi-particle breakdown. It's showing you that there's perfect Luttinger theorem all the way up to, even when the quasi-particle residue is extremely small, there's perfect Luttinger theorem. And we don't fully understand yet what's going on here, although we have some theoretical ideas. So here we expect another Fermi liquid with an asterisk, if you wish, with the smaller Fermi surface. Yeah.
So, sorry, Subir, for this remedial question, but does Luttinger's theorem hold in the SYK model? I'm sorry, I haven't thought about it.
Yes, so there's an extension. So I think the modern understanding is that the Luttinger theorem is best understood as sort of an anomaly. It's because it relates a short distance property, a short time property, which is the density, to a long time property, in which in a Fermi liquid is the size of the Fermi surface. In a disordered system, or even in SYK, there is still the same anomaly, and what that ends up doing there is it relates the particle holo asymmetry of the spectral function, this thing which I write with that theta angle, to the total density. And in the holographic language, that's actually very straightforward. Luttinger theorem is nothing but Gauss's law. It tells you that if you measure the electric field around the black hole, that just gives you the total charge inside the black hole. So those are all statements of the same thing. They're connected. So Gauss's law in electromagnetism, in holography, becomes this anomaly in the SYK model. It's not present for the Majorana SYK model. Yeah.
Okay. I see. I was just about to say that, actually. Okay.
Yeah, I see.
So the Majorana, okay, well, all right, since we did ask this question. Okay, so for the SYK model, if you look at the Green's function, it's just 1 over square root of tau. And I think there's a phase factor here, which is e to the I pi over 4. That's the Majorana SYK model, okay? But if you take the complex SYK model, this has a theta. Okay, and now there's a relationship between this theta, this is as tau goes to infinity, and the charge Q, which is C dagger C, which is an equal time correlation function. So Q is some function of theta.
Yes.
And this is a complicated function that we actually, George Parkle and I obtained it a long time ago. It's a known function. And this is the statement of Luttinger's theorem.
Sorry, Subir.
Oh, I should stop. I'm sorry, I should stop sharing. Sorry. Yes, yeah. Now you should be able to see me better. Sorry about that. Yeah.
Okay.
Okay.
I see.
So all right.
I see.
And now what happens in the holographic dual, you have the ADS2 metric. There you have the vector potential A is equal to some electric field divided by zeta, okay? This electric field is, of course, just determined by the total charge. And in fact, E is just some function of theta. So E is known to be some function of theta. That's just a translation.
Okay.
So what is Gauss's law in here is the Luttinger theorem in the SYK model.
I see. Okay. Thank you.
Sure. Okay, that's now I'll share again. This Luttinger theorem I'm talking about here is nothing to do with what I just mentioned. this is, Fermi liquid state. So, I mean, it's related, but it's not these statements. And I won't go into the details here. Another thing they can measure is the DMFT result, is some measurement of basically a transport scattering time from the imaginary parts of energy. And very nicely, you see right in the Fermi liquid, it's d squared, and right at the critical point, it has this Planckian behavior. And even this number here is very close to what you see in experiments. They get a number around 1.4, which is what you see in the experiments. Okay. All right, so that's the summary of the numerical data. And as I've already said, it leads to some phase diagram that's roughly consistent. Phase diagram that I showed you. So now, in the remaining time, how do we understand this numerics? What's going on? What is the best way to understand it? And there is SYK physics, but why is it only at one point? And can you understand the rest of the phase diagram? And what's really the missing ingredient to just starting with the SYK model and saying, okay, this is cuprate physics. That's too naive. So the missing ingredient, as I've emphasized, is this local constraint. And so what I want to show you now is that if you apply the local constraint in a certain approach, that you can understand what's going on, at least we think we can. And the key is to use fractionalization, or let's say a Parttime representation. So that's what's missing from the pure SYK model. It doesn't have fractionalization. It doesn't have any emergent gauge field, only has emergent gravity, roughly speaking. All right, so this is the phase diagram that I just told you the numerics have shown us. So let's try to understand it. First, we're going to understand these two phases, and then we'll come to this. So one simple way to understand these two phases is to use a fractionalized representation. Okay, so I told you there, let's just focus on a single site. A single site, there are three states, empty, up, and down. So I'm going to label those three states in terms of a boson, which is called the holon, and a fermion, which is called the spinon, because there's two of them. And so I'm going to represent this three-state Hilbert space in terms of the Hilbert space of a boson and a fermion. Of course, the bosons and fermions have a much bigger Hilbert space, but there's a constraint that F dagger F is plus B dagger B equals 1. So that's the new, so instead of having an inequality, I now have an equality. So this is a Parttime representation. And once you have this constraint, then you have a U1, emergent U1 gauge symmetry. These are just fancy words, but useful in some ways. You can think of this as a bigger spin. Initially, if you think of spins as two states, this is a spin with three states, but it's really a super spin because there's a fermionic operator that takes you from one of these states to the other one. So in this representation, the electron operator is like a superspin rotation operator. It rotates from boson to fermion. And the spin operator just rotates between fermions, so it's a bosonic operator. And so this electron operator and the spin operator are elements of this SU1/2 superspin algebra. There's one more element, but yeah, okay. All right, so this is, formalism, but it's the big advantage is that a non-holonomic constraint is replaced by a holonomic constraint. This is equal to 1. Okay, so now if I take this representation and put it into the Hamiltonian, now you see something very interesting. Whereas previously, these were all, I had a 4 fermion term and a 2 fermion term. Now I have a 4 Parttime term and a 4 Parttime term. So these two now are an equal footing, and it's not immediately obvious which one's going to win. And in fact, that's the whole secret. Once you do it this way, then you can get them to balance out at a critical point where, in fact, you do get SYK physics. So you have to take an SYK model of partons, not of electrons. So we'll get to that in a minute. However, another another thing very important thing to understand is that this Parttime representation is not unique. I could equally well have made the hole or the holon a fermion and the spins a boson. And so then everything would just go through in exactly the same way. In fact, this would obey the SU2/1 algebra because there's two bosons and one fermion. And this is the same algebra. In fact, you can just check that these two algebras are identical to each other. And so this is a perfectly legitimate way of writing down the theory too. So there's two different Parttime theories, one with fermionic spinons and the other with bosonic spinons. Okay. So this is all, of course, well known, but I'm just reviewing it even in a more general context. But this turns out to be very useful, the fact that you have two of them in understanding the phase diagram. All right,
hello?
so let's now.
Sorry,
yes.
sorry to interrupt. So this SU, 2/1 is obeyed for any TIJ, JIJ, or if I mean, like, is it a symmetry of the
It's an algebra of the operators. It's not a symmetry of the Hamiltonian. The Hamiltonian is not invariant under supersymmetry.
Right.
It's just an algebra.
But is there a relation between TIJ and JIJ I can impose so that it is? Or
you also have to have another term. Yes. So that's discussed in papers with Darshan Joshi. You add another VIJ term. And then if you take TIJ and JIJ and VIJ at a certain value, then the Hamiltonian has the full supersymmetry. Yeah. But
okay, thank you. And then that's a nice model somehow, or does it have similar phase diagram?
We haven't studied it very much. Also, the TIJ and JIJ have to be correlated with each other. You know, they're not independent random variables. So we haven't studied that very much. Yeah. But it's fine-tuned. I don't think it's generic. We think it has relevant operators away from that point.
But does it have a similar phase diagram? Do you know, or did you guys study the phase diagram?
I don't know.
Okay.
We haven't studied that.
Okay, thank you.
Yeah, we haven't studied that. Yeah. Okay, so this is the two phases I talked about. And then so I want to think about these phases in a very simple way. So just focus on a single site, and then there are three states on a site. And let's imagine that at large P, where you have lots of holes, the whole site is lower in energy in some grand canonical ensemble of the superalgebra. And here the spin sites are lower in energy. So this is sort of like a Zeeman term. You have the super spin. And here the Zeeman term prefers the whole site. And here the Zeeman term prefers the spin sites. Okay. And let's say that right at criticality, there's no Zeeman term and the three states are degenerate. This is a very crude starting point to understand the phase diagram just by thinking about a single site. And what's the density when the three states are degenerate? Well, that's 1/3 because the number of holes is 1/3. It's 1 out of 3. And that's actually fairly close to where we see the critical point in the numerics. So that's already telling you something interesting happens at 1/3 in this model, around 1/3. All right, so now here you have these three states of the superspin. One is lower in energy than the other two. So which Parttime representation should I take? Well, of course, if you took either, you can take either principle. And if you can solve the problem exactly, then go right ahead. But we can't solve the problem exactly. We're going to make some simple approximation of what the Parttimes do. So if you have a site that's lower in energy, obviously the thing you want to do is make that site a boson, because if it's a boson, you can put lots of particles in that low energy state and gain energy and get in a simple approximation, get a low energy state. So that's it. So that's what we're going to do. So on this side, we'll use Parttime representation 1, where the holon is a boson, and we're going to just condense it. So if you condense the boson, then you break the U1 gate symmetry completely. And you just, in fact, if you look at it, you've got these carriers that have density 1 plus P. You just get Fermi liquid behavior. And this boson doesn't carry any symmetry quantum numbers, so nothing is broken. And you just get a Fermi liquid with all of the right properties. And this is the 1/2 theory. On the other hand, here, you want to make the spins the bosons. Now when you condense these bosons, these spins have a there's a gauge invariant object, which is the spin operator, and that will have some random orientation depending on what phase you condense them, and give you this long time correlation function. And the number of carriers will be the fermions, the holes, which will have density P, but they'll form some kind of Fermi liquid with density P. So there it is. You get very simply, by using different Parttime ways of thinking about it, either the spin glass phase or the Fermi liquid phase. And finally, the thing in between, well, here, of course, we can't solve it, but we can solve it from either starting with this theory or that theory, and we get very similar results. But we have to introduce another parameter, and from this theory of SYK of fractionalized excitation, we in fact get exactly what's seen in the numerics, the 1 over tau decay of spin correlations, at the same time, the 1 over tau decay of the Green's function. But notice, naively, you would think that, for any kind of metal, the spin correlation is the square of the fermion. Here it's not, and that's really what makes this a highly non-trivial state. Okay, so how does this work? Well, it's, you just generalize the SU2 symmetry to SUM. Then you have these four Parttime terms, and you just do the usual SYK approach. You get, Dyson-Swinger equations, and sigma is G cubed. Okay, then now it's some mixture of fermions and bosons, and okay, these kinds of things have also been studied in the SYK context recently. So you can solve all of this and get pretty much, this type of behavior. In particular, when you solve these equations, you find that the leading behavior of the Green's function is 1 over square root of tau. So any bilinear operator of fermions or bosons give you 1 over tau decay. And that's what the spins are. The spins and the electrons are bilinears. And so that's why they have this highly non-Fermi liquid-like behavior. You get the 1 over tau. Okay, and then you can ask, what are the corrections to the leading behavior? So these are, very much SYK-like corrections. The leading correction to the Green's function is 1 over tau correction. And this is intimately connected to this time reparameterization soft mode, which is the boundary graviton, JT gravity. So that's the correction. And now if you take this model and in some finite large D generalization, you compute the analog of the resistivity, you find indeed you get a linear T correction coming from this term, whereas the leading term gives you a constant. And down to 0 temperature. So
can I ask you a question,
really
please? Sorry.
Yes.
I'm sorry. This Green's function FB that you wrote. So it's it's a new charge neutral, like F dagger B type of thing.
Oh, sorry. There's I apologize.
What is
so there's two Green's functions. There's GF and GB. So stop share. So GF, is F dagger, and GB is BB dagger. Okay. And this is just, and these satisfy these equations here. Now I have to share. So GF and GB that I wrote on the screen, they obey these equations. And everything I'm telling you in the next slide informally contained from the solution of these equations. Oh. But as you know, the solution of these equations is incredibly rich. The leading behavior is the square root of tau. This is just like in the Majorana SYK. Both the fermions and the bosons have the same 1 over square root of tau. And also, like in the Majorana SYK, the first correction is 1 over tau with a coefficient, which is called alpha G by Maldacena and Stanford there. So we just call it alpha F and alpha B because those are two different numbers that we can, in fact, compute from, the coefficient of the Schwarz chain or the value of the boundary graviton. So it's just only one parameter, which is the coefficient of the Schwarz chain, from which you can get alpha F, alpha B, and also this coefficient of linear resistivity. They're all related to the same unknown UV sensitive quantity. Okay, so what I was just going to say, this is, as far as I know, this is really the first model where anybody has found linear resistivity down to 0 temperature. I mean, you can get linear resistivity at high temperatures, but this is at least in this large M limit of SUM. So there's like a double scaling limit here. First, you take large N, and then you take large M, which was actually already present in my first paper on this topic in '93. It's the same type of scaling limit. And for the TJ model, it gives you this linearity resist. I mean, we didn't understand this correction term in those days by any means. And now we can look at this correction and gives you exactly what you see.
So, sorry, Subir, can I ask just one or two remedial questions, if you don't mind?
Please. Sorry.
No. What is M? I missed what M was, the parameter. Sorry.
Yeah, I didn't write it down. Sorry. This is, trouble when you take your old talk and you massage it in different ways. Right. So, yeah, okay. So this, yeah, I apologize. I didn't write it down. So this theory, the TJ model theory, has an SU2 spin rotation symmetry. Okay, alpha goes from 1 to 2.
Yeah.
So you take a model, roughly speaking, where alpha goes from 1 to M.
Okay. I see.
So first you have N sites with spins and fermions of SU2 on those N sites. You send N to infinity. Then you get these equations that I showed you earlier, where you have to solve numerically a very complicated impurity problem. Then you take SU2 and generalize it to SUM. So here it's like a SUM/M prime theory. Okay. Then take that large M limit. So after you take those two limits, then you get SY. Then you get, when the dust settles, then you get everything reduces for the TJ to these equations. So these simple SYK-like equations only appear in the large M prime limit.
I see.
Now, I should also say, however, some of these results we can obtain without taking the large M limit by a certain RG argument. There's a certain, that's in our PRX paper. I'm not talking about it, but there's reason to believe that at least for the critical exponents, there are no 1/M corrections, that the large M result is exact. And I'd have to refer you to our papers for that.
Okay, great. And then if you can just go to that slide where you have the resistivity going linearly with T.
Yeah.
Now I'm a little confused, sorry, because of course in the JT model, the specific heat goes linearly in T and all, due to the boundary gravitons, as you say. But here, this is the electrical resistivity. This is the resistivity, right?
Yes.
And I was just trying to map it. I mean, even if you put a phase mode in and so on, I mean, is this something I should know from the JT? Sorry.
No. This is, so first of all, you have to define what is the resistivity.
Yeah,
okay.
That's right.
So the resistivity, first of all, you have to have some sense of space to define resistivity. This is why I said you need a large D model. So you have to take a slightly different limit where you have a lattice and high dimensions rather than a fully connected cluster. And then you use the Kubo formula there. And once you use the Kubo formula, the resistivity turns out to be basically some sort of integral over G squared with some spectral density here.
Oh, I see.
So it's some equation like that. And so basically you take this G and you put it into this formula that you get from Kubo formula and just evaluate the integrals. So basically the step from where holography and other things come in is to get this answer.
Okay.
Once I have this, then from here to here is some messy solid state physics.
I see. Okay.
Okay.
Thank you.
So this is I guess I most clearly stated in paper by Maltestin and Stanford first. This correction term, and this correction term, which comes from the graviton, is exactly what gives you in the end this linearity resistivity.
I see.
It was very exciting when I first realized that. Yeah, there's no reason it had to have worked out that way, but it does. I think it's quite non-trivial.
Yeah, I see. Thank you.
So for example, we can also, I showed you the spin susceptibility that we measured in the numerics. And I showed you it had this form, a constant, discontinuity at omega equals 0 and a linear in omega term. And this is what you get from in this model and also the SYK model. And this linear in omega term, this term here is the contribution of the boundary graviton. So in this paper with Maria Hayu and Grisha, we worked out, well, they worked out really many additional terms, and they fit the numerics from the SYK model, that's the red line, extremely well. And also, and results are very similar to the numerics of the critical point of the TJ model, which is really quite exciting. Yeah, so this is what I'm referring to, this is now not a large M or any limit, it's just the TJ model on a fully connected cluster. Okay, and you can also extend this to finite temperature, and you get this Planckian time appearing here and also in many other properties. But this is where we have computed this in great detail. And this is the correction from the graviton. Okay, so that's pretty much the end of my talk. So the summary then of the main points. So we studied the random TJ model. You may or may not like it, but we think it is like a minimal model that doesn't fully throw out the baby with the bathwater. And the reason it's, I think, very, very useful to study it is because it retains this local constraint. And that local constraint, in turn, leads to the existence of an insulator, leads to the existence of a pseudogap phase, all of which simply don't exist in the ordinary SYK model. And even this very simple model, this minimal model, has, seems to capture, to me, a surprising amount of physics accurately that you observe. First of all, you see the pseudogap phase all doping. At least in certain materials, there's spin glass order observed. And so all the general zeroth order characteristics of this phase are correct. And this phase, as I said, is just absent in the SYK model of any type. Fermi liquid at large doping, but somehow Planckian metal behavior, right, with this KT over H bar linear T resistivity appears right near the critical point, exactly as seen in the experiments. And this is very much connected to SYK criticality, as we've argued. Yeah, so this is what I mean by SYK criticality. It's a generic system with many body chaos in terms of H bar over KT. And this is the simplest system that obeys this, the pure SYK model. And now we think the TJ model near its critical point has similar behavior. We have only shown that in the large M limit, but there's numerical evidence it still holds even for M equals 2. All right, and there's a dual holographic representation of the simplest SYK criticality, where this leading irrelevant operator is connected to the boundary graviton of 2D quantum gravity on areas 2. And this is what I talked about, where this comes from this, I reviewed in my talk on Monday, if you want to know more about this. And this boundary graviton was also very useful for understanding the TJ physics. For example, what you see at the critical point is this spin susceptibility with this discontinuity at 0 frequency, and then this 1 over omega correction. And this comes from the graviton, this correction here. And the same graviton also gives you linear T resistivity in the random TJ model. And if you apply it to black holes, and generically any kind of charged black hole with Einstein gravity, the leading term is the Bekenstein-Hawking term, say 1 over G expansion, or G expansion. That's area over 4G. And the first subleading correction to that is universal. And this is given by the path integral of this boundary graviton. And this -3/2 1 over log P that I believe applies to any generic black hole without supersymmetry, which is in this extreme low temperature limit. Okay, I think that's all I have to say. Thank you very much.
Okay, thanks a lot, Subir, for the good talk. Any more questions for Subir?
I have one question, Subir. Is there some way of understanding going away from SYK criticality by turning on some operators?
Yes, so in the large M limit, that's kind of what we
Yes.
get, or even we have an RG analysis too. So, but we have to apply it to this. Okay. Yeah. So if I take, the usual SYK, where I just take the SYK for fermion term and add a 2 fermion term. That 2 term is a relevant perturbation and just always takes you away from the SYK point. And it takes you to a Fermi liquid. And that's, that's not what we want. Okay, and that's part of the purpose of my talk, is to show how do we repair that problem, that we get not just a Fermi liquid. You should be able to, first of all, have a critical point where nothing is, where you can tune to SYK down to 0 temperature. And then on the other side, you get a pseudogap like phase. That's what we want, okay, to understand the experiments. And the way you get that is not in the usual SYK, but in this kind of model, where you do the Parttime representation, and then you write it in terms of bosons and fermions. So there are these are both 4 Parttime terms. Now this theory, unfortunately, is not solvable immediately. You have to take this large M limit, which I should have been a bit more explicit about. Sorry about that. But if you take the large M limit and then ask what happens, well, what you find if you take the large M limit, then there is a term here, which is a chemical potential term, which changes the density, which I haven't, which basically changes, it's this Zeeman field term. So the tuning parameter in the end is this chemical potential, which is like a B dagger B minus F dagger F term. So there's a term which is basically, like a Zeeman term, which is B dagger D minus F dagger F. So when it prefers the holon, then this is the. So the relevant operator is the chemical potential between the fermions and the bosons. So when it has one sign, you go to the disordered Fermi liquid. If it has the other sign, you go to spin glass. And if you tune it in a narrow window or at exactly a critical point, depending on which particular limit you're looking at, you get SYK physics. So the short answer to your question is you take a SYK of bosons and fermions mixed up, and you have a chemical potential which tunes the relative density of the bosons and fermions. That's what you need to get the basic phase diagram.
I see. Okay. Thank you. Thanks.
So, sorry, Subir, can I ask a question about just that slide of yours?
Sure.
So because you worked in terms of the partons, you had an emergent UN gauge field, which I saw got gapped on the disordered Fermi liquid side because the boson, which was charged, condensed. Correct. If I understood right. Yeah. But on the metallic spin glass side, what happens? Is there an emergent U1 or is it gapped also?
It's also gapped because a different boson condenses. This is why you have to flip the partons. Yeah, I mean, so I lost Sandeep. Yeah. I think Sandeep.
Sorry, my internet failed.
Yeah.
I'm sorry. Sorry. Is there a gap? Is mass gap for the U1 gauge boson on the spin glass side also somehow? Which I didn't see why. But...
Yes, there is, because here also you condense a boson. You just condense a different boson.
Oh, I see.
Condense this. You flip to the other theory. So so okay. It is true that. So when I choose, what I'd love to have is a theory that works everywhere and I can solve it in some limit. Unfortunately, I don't have that. We don't have that.
Okay.
You can take this SU1/2 theory and take its large M limit it'll give you this phase and this phase.
Okay.
You can take this theory and take its large M limit, it'll give you this phase and this phase. And then you can see that the two of them are consistent in between. That's kind of what we can do.
Okay. I see. I see.
We don't have a single theory that gives you everything in one fell swoop. That would, of course, what you want, but that's only the numerics can do that.
No, that's fine. Thank you. Sorry, I was confused. Thank you.
And we have another RG argument, which in fact shows without the lot that these two theories are identical. That's over here. And we can compute perturbatively the RG away from this critical point. And that's actually most of this PRX paper, which I didn't discuss at all. Anyway, so it all hangs together very nicely, I think. But we don't have some, SYK-like equations, which in one fell swoop can give you all three phases. You have to play a little bit.
Okay.
Hi, is this infinite U limit necessary to go to the Parttime representation?
Well, I mean, it should be large, I would say. Yeah. I think you basically, if U is not large, you will never get an insulator or a pseudogap. You'll just be on the right-hand side, pretty much. Which is what was done in the earlier days. You'll be on the right-hand side, where at higher temperatures, you might see some crossover into this critical behavior, but you'll always be on this side.
So was that what happened with this numerics you showed with some non-infinite U?
But it was still large. It was large enough that we got phase transition.
Right. Was it the same thing you said can't access the spin glass side?
But it's there. They see something breaking down. They can work up to this red line. They can't go below that because they see something. The whole equation just breaks down. But so there is definitely a spin glass phase. They have a lot of evidence for it. This is at U equals 4 times T. This exact diagonalization, we can go right into the spin glass phase at 0 temperature. That's why we get delta function. This is done at U equals infinity. Now, for this exact diagonalization, it's actually preferable to have U equals infinity because you have 3 states per site rather than 4 states per site. And 3 to the n is much smaller than 4 to the n when you're exact diagonalizing. So that's why we prefer to work with U equals infinity. In this DMFT numerics, they don't want to take, because their quantum Monte Carlo algorithms don't work well at U equals infinity. So they take U at some large value. But you notice that, for example, consistent with what I just said, their critical point is around 0.2. And our critical point was around 0.3 or 0.4. So as you decrease U, the critical point is moving. And I would suspect that when U becomes, small enough, it'll just disappear. The spin glass will disappear, but it hasn't disappeared yet at this point.
Right, and also the carrier density we had from the 2 phases, like does that match numerics or the P and 1 minus P?
No, at this point from the numerics, we haven't quite come up with a way to diagnose the carrier density. This is exactly the point we want to think about now. Yeah. So we're working on that. I haven't quite figured out how to do that. It's a question, how do you define a carrier density in an infinitely connected cluster? And how do you define a Luttinger theorem? We're sorting it out. Hopefully we will soon. Yeah.
Thank you.
I have a simple technical question, Subir. This operator conjugate to the chemical potential that you mentioned, B dagger B minus F dagger F.
Correct.
In the other representation, in the sort of dual representation,
That's right. Yeah.
It's the same operator. I mean, you can write the same operator.
F dagger F minus. Yeah, it'll be F dagger F minus B dagger B or something. Yeah.
Okay.
So what we could show in the RG that you take this operator, you can write it as B dagger B minus F dagger F in one form, or F dagger F minus B dagger B in the other form.
Yes.
With both forms, if you compute the correlation functions all to any order, you get the same answer.
I see.
Yeah.
I think that's quite important, right? Yeah.
Yeah. No, there's several appendices in our paper showing how that works out. And basically, the point is, the simple answer, it looks fancy, and in the end, you can even write it down as some duality between two Wess-Witten terms and so on. But ultimately, the statement is very simple. Any kind of correlation function you're computing in these local objects, it only depends on the commutation relation, on the algebra. Anything, the full time evolution of any operator is just fully dictated by the algebra of certain operators. And as long as the algebra is the same, your answers have to be the same. So it really is. So once you show that the algebra are the same, which we did show, once the commutation relation of all the generators of these two groups are shown to have exactly the same, even though they have different representations in terms of F and B, the commutators are exactly the same. So then you get the same answers.
So in some sense, would it be correct to say that if I write a path integral in terms of one representation, I can actually, I can do some manipulation and rewrite it in terms of the other representation? Looks.
Yes. I mean, if you write it in terms of a path integral, what happens is, this is the fanciest possible way to say it, so I'll say it. This, goes back to Witten's original paper on where he introduced at least the modern form of what's called the Wess-Witten term. He takes a single spin on a sphere, write down the Wess-Witten term. So that's exactly what we do here. Also, you have a term d tau, some a of tau, a of some s. This is like the vector potential ds d tau, which you can manipulate into Wess-Witten form. And here S belongs to SU1/2 or SU2/1. So if you take the specific path integral over these two super algebras and put it in here, they look very different. But then you can just check that the commutators, the algebra of the operators are exactly the same. So they're the same. But it's a highly from the path integral point of view, it seems like a highly non-trivial statement, because you can't do this path integral. It's a complicated integral. Even for an SU2 spin, we can't do that integral, as you know.
I understand. So basically what you're saying is that because the algebra is the same, the coadjoint orbit on which this the path integral is being formulated is identical. That's one way of putting it.
Okay, I'll pretend to know what a coadjoint orbit is, but I think that's correct.
Okay. Okay. Thank you.
That's
so
correct.
much.
Yeah, you just said that in a much neater way, I think, than I did. Yeah, that's what I was trying to say. I should try that next time.
I have a couple questions.
Sure.
Can I ask a couple? Yeah. The first question is in your Parttime. In the Parttime construction, you get PC is equal to 1/3. Is that coming from some argument or from a detailed calculation?
It's okay, yeah. So the answer is yes, I guess that's the honest answer. So I was making this picture here, just even before you get to the Parttime representation. In fact, it doesn't rely on the Parttime representation in the end.
I see.
There you go. Here it is. Yeah. So I haven't actually put any Parttimes. So there's an RG calculation that I didn't describe, and that RG calculation is basically doing this path integral over here for a single spin with some couplings perturbatively. And again, you can do the path integral over these coadjoint orbits exactly because you can just reduce it to evaluating a whole bunch of commutation relations. Okay. And So in that RG, what we find is one relevant operator. And the RG is an expansion in some epsilon expansion, which I don't have time to define. And to zeroth order, PC is 1/3 in that calculation. Yeah, when these three states are exactly degenerate. Then there are corrections at higher orders to PC, and yeah. But yeah, we're thinking about those corrections these days. Yeah.
I have one more question. How is the spin glass phase connected to the antiferromagnetic phase at zero doping in experiments and probably in theory?
Yeah, so the antiferromagnetism is really, of course, a feature of the system without disorder. And I mean, in the experiment, you can see for yourself, there's always even, it depends a little how good your crystal is and so on. But I guess what they're saying here is that if you're at very low doping, it's like a disordered antiferromagnetism.
I see.
Okay, my headphones just died. Can you hear me now? I can't hear you.
Yes, I can hear you.
Can you hear me?
Yeah.
Okay, sorry,
Yes, I can hear you.
Yeah, my headphone battery just died, so now I'm back, I hope. Okay. Right, so I was saying, yeah, over here it looks like a disordered antiferromagnet, but from neutron scattering, then you don't see any antiferromagnetic moment at pi after a while. But from NMR, which is more a measure of the local moment, you see glassy behavior all the way up to PC.
I see.
So antiferromagnetism, NMR can't really tell the difference between antiferromagnetism and spin glass because it's not sensitive to spatial structure, but neutron scattering can. Yeah, so this model doesn't have, it will be a spin glass at zero doping. It won't have ferromagnet. So in fact, at zero doping, this is the original SY model, which we've been known for quite a while, has a spin glass phase at zero. Well, spin glass for SU2.
Okay, thank you.
Sure. Okay. Okay.
Any more questions for Subir?
Sorry, Subir, can you just ask a quick question? Like,
sure.
Can you say something about what is the like how does the specific heat behave or entropy and so on? So you made some statement about the entropy in the black hole and so on, but in these three phases of this TJ model, like how does S go as a function of T or C goes?
Yeah. So all right. So in the Fermi liquid phases, you have both the spin glass and the critical and the Fermi liquid. You get entropy going to zero, linear temperature. Now at the critical point in the numerics, this is something we studied. I didn't show the data. We studied if it is really SYK, you would expect a zero temperature entropy. So it'll be S0 plus gamma T, not just gamma T. So we look for the S0, and if it's present, it's extremely small. We couldn't see it in the numerics. In the large M limit that I described, there will be an entropy, S0, but that's the large M limit. Yeah. So ultimately, I think that there is no entropy at zero temperature, and this SYK behavior is preempted by something else at very low temperatures. But so far in the numerics, we haven't seen any sign of that.
Okay, thank you.
Sure.
Okay, so if there's no more question, maybe we can thank Subir for the great talk.
Thank you very much.
Thank you so much. I'll end the Zoom meeting now.
Thank you.
Bye. Bye, Spencer.
Bye. 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 Bye.
Bye.